Now let's have a look at the internals of a frequency mixer. A block diagram of a mixer is shown here. You know that the central element of a frequency mixer is a multiplier, which multiplies the input signal with the carrier and then produces the output. In this example here, we use voltage signals. So there's an input voltage signal and an output voltage signal. And here there is an oscillator. And this oscillator is on in the receiver or in the transmitter, so it is in the local device, so it is also called local oscillator, or in short LO. So this is why we now name the voltage signal of the oscillator ULO. And here you see the mathematical description, which shows the multiplication in the time domain. And remember, this resembles our double sideband with suppressed carrier amplitude modulation. Yeah, so this is the background of our mixing. Now let's switch to the frequency domain. You know that the multiplication in the time domain gives a convolution in the frequency domain. And as we have considered the case in the transmitter in the previous videos, now we have a look at the receiver side. So you have an RF signal here. So this signal contains the information modulated to the RF signal. And now here is the monochromatic signal of our local oscillator. And now our frequency mixer does multiplication in time domain, and this is a convolution in the frequency domain. So you see here that the signals are even symmetric because they are real-valued. We still consider real-valued signals here. And yeah, now let's see what happens. So the convolution leads to shifts in the frequency domain. So at first, consider this part of the local oscillator signal. It shifts this part of the RF signal up, and this too. So an upshift here means that the center frequency is increased. And the negative part of the local oscillator signal also leads to a shift in the frequency domain, but the center frequency is reduced. So again, the mathematical derivation is described in the lecture notes. It is also important to understand what happens here. So please also read the lecture notes. And now on the mixer output, we have this situation here. You see that the signal is still even symmetric, and therefore it is still real valued. And now we have two duplicates of our original RF signal. And this is the problem with mirror frequencies. So we have to filter out one of the duplicates here. Filter is also applied here to meet the symmetry rules. And now we can use this signal. So this signal is filtered out. So this part of the signal is filtered out. And then we can use the remaining part and pass it on to the next stages in the receiver. What you have to keep in mind that the mixing process produces two duplicates of the input signal here. So this is the input and this are the two duplicates. Now let's see how to cope with mirror frequencies. So the problem or the original situation is described here. And we have two signals. So the green one is the signal which we actually want to receive, and we want to convert this signal down to the baseband here. So we take a local oscillator, tune it to the frequency, which will then become here our zero frequency. So the frequency shift, so the frequency difference is then what we want to see here. So our green signal should be converted to the baseband here. And this is the difference between the carrier and the center frequency of our green signal. But there's a problem. There is a second signal nearby, which has the same equal frequency difference, but just mirrored. So whereas this frequency difference is positive, this frequency difference is equal but negative. And now let's have a look at the output. This green signal is indeed shifted down to the baseband, and now we have left out the negative half plane of our spectrum here in this example, but you have to keep in mind the negative part, especially the local oscillator signal here. And we also have the situation. And now remember that we have two duplicates. So the duplicate of the green signal is not depicted here, but no, sorry, it is depicted here. So actually, this was wrong. So let's do it again. So the green signal is indeed shifted down here, and the duplicate is here. Sorry, that was a mistake. And now let's consider the yellow signal. There is a first copy here, but the second copy just falls into the same baseband as the green signal. So there is an interference. And this is the problem with the mirror frequencies. So if you then apply a low pass filter in the baseband, which should actually filter out our baseband signal and remove all other high frequency disturbances, we still have the mirror frequency of the mirror frequency problem, and we have the yellow signal here in the baseband, which overlaps our green signal and interferes it. So what is the solution? You have to apply a filtering before down conversion, so before mixing the green signal down. And this filtering is usually done in the IF stage. So there's an intermediate frequency stage where the filtering is applied. Because here in the original signal, the two signals are so close that it is hard to find a good filter, or good filters are expensive. So this would be a normal filter here, and it is useless because it does not filter out the yellow signal reliably. But however, the filtering can be done in the intermediate frequency stage. So there are of course other technical solutions. You can of course use an expensive high quality filter. But now let's consider that you have an intermediate frequency stage to filter the green signal out, and then it should be no problem to have the two duplicates here. One duplicate is in the baseband, apply low pass filtering, and now that you have reconstructed the original signal which you want to use. So, and let's come back to this picture here. The problem with the mirror frequencies is why analog modulation techniques prefer this quite complex super heterodyne receiver design with an intermediate frequency stage where the filtering, the high quality filtering, can be done. So this is again just a simplified design, so actual receivers are far more complicated. Yeah, and the same goes for digital modulation. You can find receiver designs with one or more intermediate frequency stages, but at the end of the lecture we will come back to this receiver design and we will extend it, and we will see how to use this design without an intermediate frequency stage to decode or to downconvert RF signals directly to the baseband.